All right, welcome to another exciting edition of AP Chemistry here at Spin Park. First off, on the lab, are we comfortable as far as what we need to do on the lab? Okay, everybody, no questions. You know, hopefully the video that I did yesterday just kind of helped clarify just the step-by-step of what needed to be done, okay? And so then you have the post-lab questions that you need to answer. So today, well, obviously you're not going to be here till Thursday, and with a lab like this, we're going to turn in the perforated top copy to me. So I guess since I won't see you again until Thursday of next week, is that's when it will be due. Okay, and the other class, I guess I have to give them till Friday to turn it in. And the virtual kids will turn it in on Thursday, and they'll just have to do it. Virtual, you guys gotta do it on a separate sheet of paper, just kind of list your data table, and then CAM scan that in and submit it on Classroom. I'll make it an assignment. Okay, but for everybody else that's full-time, face-to-face, just you'll turn it in on Thursday, the actual perforated copy. Okay, it's a lot easier for me to look at that and grade that than on a screen. Does everybody CAM scan now? And you should learn how to get it all on one page. Okay, some of y'all are putting it in on 2 pages and whatever, and it's not that big a deal, but it's a lot easier if you can make it to where it's all on one page. You know, one file. You know, 2 or 3 pages, but one file rather than 2, 3 separate files. If you don't know how to do that, maybe ask a friend, because I've never done it, so I can't really tell you how to do it. I just know it can be done because 75% do that. And that's just a free download, isn't it, onto your phone? Does it work on Android as well? Does anybody know? Does anybody have an Android?
You can just use Google Drive on Android. Like, it'll work directly with Google Drive.
Oh, well.
For some reason on iPhones it doesn't work.
Yeah. Okay, so there's ways to do that. So it just makes it easier when we do turn things in if we can do that. Again, you can have multiple pages, you just put it all in one file rather than multiple files. All right. So far we've covered the atom, the discovery of some type of particles with J.J. Thomson in the cathode ray tube. We've talked about Rutherford's gold foil experiment and watched that exciting video on that. We've talked about atomic number, mass number, and how to calculate average atomic mass, okay, all in chapter 2. And then we've gone through and done percent composition and empirical formulas. And then included in that, we did the empirical formula of a hydrate. So to kind of get us started, I want to go over the worksheet that you guys turned in by, I think it was, did I say 8 o'clock this morning? Okay. Well, I was due yesterday, but then I extended it yesterday on a statement in classroom that said, you know, I won't count it late. I keep screwing up on 6th period. I either put it in virtual or I don't click and I post it in 1st and I don't post it in 6th. And I'm just too old for this stuff. So anyway, but let's look at that worksheet. So I need y'all to go ahead and put it on the board. So who will put 75 on the board for me? Nobody has confidence on 75, 76, 70, I'm gonna call on you up there, so 76. Okay, Paul, thanks. Okay.
I'll do 75.
You'll do 75?
Here, I'll do
76 is the performance.
Yeah.
It's supposed to be done, though, you just put it up there, okay? 75, she volunteered first, you'll do 76, okay? Ben, you get 77. Just come put them up here on the board.
That's why you have 75. I knew he was going to do the other part. So might as well say equal.
Let's go in order, so 75 over here. Show the work, right big enough for people to be able to see it, both here and starting with a clean slate. Hey, are you guys planning ahead now on which one you're gonna get to? Okay, so 5, is this everybody? I'm sure you guys noticed that I did put the actual grades into iNow yesterday, so everybody here has basically got a 100. I'm liking what I'm seeing. Yeah, it just depends on what you used as far as the molar mass, how many you used in that, so. Did you, I mean, like for, which one are you talking about
Like, I'm
specifically?
getting, like, if I rounded the same, so like for poles, instead of 3.3, I did 3.41, and then for the next one.
Well, what was the given in A, he has 60 milligrams written, is it 60.0, is it, what's the given there? Yeah, you have a sheet. That's what's gonna determine it,
Oh, okay.
so it's number 76.
Yeah, so it's just
60
60.
with a decimal
Well,
point,
yeah,
right?
it's got a 6.6.
Okay, so that makes it 2 sig figs.
Okay.
Okay, so you always have to use the given as well as your conversion factors, for that. Okay? So we got the molar mass. And it's 5%, right? Isn't that what it is? 5%, that's that why you did that? Okay? Divided by the molar mass, gets that many moles. Molecules. Technically, you could just use, Ben, you could use your 2.878 answer from B
Okay,
and not have to show the division again,
alright.
because you already have moles and just go mole to molecule.
Sorry.
Yeah, yours was supposed to be the one that only had one
I
part.
know, why is it taking me so long?
Start off the question.
Yeah.
Oh. I'm kind of having to change it because I messed up, but,
Hey, Paul, will you do me a favor and on 2 times 10 to the 22nd, put what that is?
Yeah.
What you found?
I know that you guys quite forgot what I was finding, so.
That's that. Well, that's important. We're finding grams, we're finding atoms, we're finding molecules. What are we finding? So it's real important to label what you find. So if we look here now at Kruthika doing number 75, maxed in as close as I can get. Okay, you can see that she calculated the molar mass. Okay, then she you have her grams as 28.4 times 10 to the minus 6. Where did that come from, Kritika?
from the problem.
So what did it say, that it was a percent?
Yeah, it said 1.0 times 10 to the negative 4%, so you.
1.0 times 10 to the minus 4% was actually the chemical.
Mhm.
So of the 28.4 grams given, only 2.84 times 10 to the minus 5th was actually the chemical. And then to convert the grams of that to moles, just use the molar mass, which she shows the calculation for. Okay? Does everybody agree with those numbers? Anybody disagree with that number? And then sig figs. Now, when you're looking, just so you know, with sig figs, you have 12 carbons, 4 hydrogens. That's, I was thinking that was sig figs above it. But we have 12.01 is 4, but hydrogen is 3. But when you add all that together, you're going to get 2 decimal places all the way through. And so, the 3, why did you go to 2 sig figs, Kruthi?
Because it was given, because that was 28. Oh, I only went to 28.
But you on your down part, on your grams, you have 28.4.
Yeah, I think I was supposed to go to 28.4 when I actually calculated it.
Yeah, so we really probably should have one more sig fig on that.
It should be an 8 after.
8.78, okay? So Kruthi, go write that up there at 8.78, just so people we can have a definitive record for all time on our exciting video.
Wait, is to the negative 7th, right?
I got the negative 8.
Yeah, I think you said it.
Yeah, I did too.
Okay.
All right, well, I said, does everybody agree with this number? Did anybody disagree? Oh, no, it's all good. Be bold,
Yeah, I was
y'all.
like, I don't think that's right.
All right, so the setup is all 100% correct. Calculator usage is not so much correct. Okay, so number 76 goes where we were given 60 milligrams. Now the only thing I'm going to say on this particular one is if you look at the worksheet carefully, and it seems like something very small, but it's not just 60, it's 60. Okay? What does that decimal point do? Makes the 0 significant. As 60 without the decimal point, there's only 1 sig fig. But by putting the decimal point there, that makes the 0 exact. That means there's 2 sig figs. Okay? So little details, you got to pay attention. This setup here is all correct. Okay, was it exactly 1 gram, or did they give it any decimals?
It was
1.00. Okay, so don't just drop off those values, because for sig, it doesn't change the answer at all, but it changes the sig figs and what degree of accuracy can we go. So our answer needs to be the 3 sig figs, 5.68 times 10 to the minus 3 moles. So it's just a matter of carrying. So don't just drop them off because they don't change anything. They're there because they measure to that degree of accuracy. That's the whole point of sig figs. We want to be as accurate with our answer as possible without exceeding the limits of what we measure. And then again, so then this would be 5.68 moles So there are, so that's gonna be times 6 because what they're, where's the formula, do we know? Did it tell you the formula of the substance?
It did, but I didn't.
Okay, but there are 6, are there 6 atoms in the molecule? I'm assuming.
I think it asked for like the percent, like how many oxygen atoms?
How many oxygen atoms there are? Okay, 76C says, when you consume 1 gram of vitamin C, how many oxygen atoms are you eating? Okay? So this is how many moles of what? B.
Of the entire thing.
The vitamin C, right? Okay? So now in vitamin C, they tell you the formula. C6H8O6. C6H8O6. Okay? So this is going to be times your 6. So in this many moles of vitamin C, we're going to have 6 moles of water. So again, just being picky here, but we probably want to say 6 moles of oxygen for every 1 mole of vitamin C. So then the moles of vitamin C cancel. It's important that you know what you have and what you're looking for. That's why units are so important. I'm going to stress them all year long. Go ahead and use the units because it's going to tell you what you need. Now, that's going to equal how many moles of oxygen. And I'm assuming the 0.04 was the answer to that, but we need to carry it out to a little bit more sig figs. So we're going to be at 5.68 times 10 to the minus third moles of vitamin C times 6 moles of oxygen for every 1 mole of vitamin C. Okay, and that's going to equal to 3 sig figs.
0.0341.
Moles of oxygen. And now to convert that to actual atoms, times the 6.02 times 10 to the 23rd oxygen atoms for every 1 mole. And that's going to turn out to 3 sig figs again to be
2.15 times 10 to the 22nd.
okay? So, setup is all 100% right. Okay, we just got to make sure that we carry the digits to the proper degree of sig figs, you know, that we don't just drop these values off, that we carry them through all the way. Yes, ma'am?
So the place you got the 6 moles of oxygen was from the equation?
From the equation right here, because for every molecule of vitamin C, there's 6 oxygen atoms. So whatever the stuff, so if we were doing hydrogen, we do 8. If we were doing carbon, we do 6. Good question. All right? Let me just go make sure we gotta move the camera. So, and here is the final answers over there. Okay? So when we look at number 77 then, number 77 looks pretty good to me. Does everybody agree with these numbers? Okay? We calculated the molar mass of that thing, is that rotenone, okay? But only 5% of it was actually rotenone, and so multiply the given 227 grams times the 0.05, so you have 11.35 grams of rotenone. Divide that by the molar mass to get how many moles, and then multiply that mole value by, I'll guide those numbers to get molecules. Now, if you wanted to, you don't have to show this part again. You have moles calculated here. You could have just brought this value down and then just multiplied it, because this is going to give you that. So you already did it. So you don't need to redo that. Now, it's not wrong to redo it. I'm just saying sometimes time is of essence and we want a shortcut. So, you already showed your work on how you came up with moles, so you can use the moles, you just go directly here, and you did a good job labeling everything. Now, if the question was specifically gonna ask, how many carbon atoms are there? What would we do? How many carbon atoms are in this 227 grams?
We do like 23 moles of carbon.
Okay?
Or you just multiply the mixer by 23.
Just and multiply by 23. Because for units, there are 23 atoms of carbon for every 1 molecule of rotenone. Okay? We multiply by 22 for hydrogen, multiply by 6 for oxygen. Okay? So we can go to moles, to molecules, to atoms. Okay? Using the conversion factor. So grams to moles is the molar mass. Moles to molecules would be Avogadro's number, and then the formula takes us from molecules to atoms. We're all good there? All right, well, we got a few more. You guys already know, so we did, what numbers? We did 90, 92, and 93?
We did 75, 76, 77, we still gotta do 90, 92.
That's what I'm saying.
Oh, okay, yeah,
So what's left is 90, 92, and 93?
yeah.
All right, so Andy, you get to do 90, Lauren, you get to do 92. Does anybody want to be a volunteer to do the third one? It's the vanilla.
Oh, I see.
Okay. So, will you erase? Make sure if you erase completely. You can't have any stray marks. Are you coming up here to do this? Do you need to
Yeah.
get started? Because you're gonna take the longest.
I won't write the questions this time.
People at home are gonna have a lot of fast forwarding.
On the other video, like went through and clicked the right arrow.
Yeah. Well, that's the benefit of having it on video.
Instead of the Google Meet.
Yeah.
Yeah.
And if you need to take a break and, get something to drink or do whatever, you can pause it and so. And this with an iPhone is gonna be way more clear. This is how I did them all last year with, in the spring. I just made videos without anybody in the classroom.
Don't y'all get our booklets or our answers for the AP exam?
So how did that look last year?
Well, I got them all online. I could look at everybody's online.
I heard, I don't know what John Wilson got, but I know Duncan got screwed over, and then, cause he had to take it again, and then he got a 3 for some reason,
Yeah.
which, knowing Duncan, that's probably not accurate.
Well, it is accurate. I went through, I looked at, Travis asked me to go look at his, and, it was graded correctly. He was close on most of his stuff, but he just made little mistakes. And it was a completely new format. We didn't have a chance to review at all together. And so grades were just way down. Normally, again, I have 80% or so or better, making a 3 or better. And this year it was 50. So, and I only have 1 5. Normally there's in this class I was expecting there to be 6 to 8. And a bunch of 4s, and they're just, so I'm just chalking that up to a lousy spring. And okay, go right here, we're at a critical point right here that we hadn't really talked about.
I just multiplied
By what?
by
just saying, you get this here, this is gonna give you the empirical,
But it's just,
which is gonna be the same.
yeah.
Okay, so now just put your empirical formula, just write it out.
Wait, okay.
Okay?
Do I have to write out the?
No, you can just put, say what it is.
This was a molar value, I have to multiply by this by 3 now.
Yeah, but, yeah,
So,
so it's gonna be,
150,
so it's gonna be 12 times 8 is equal to 96, plus 8 is 104, plus 48, 152.16.
I think I did good.
and then we do like,
Okay, equals 1. So therefore, that's the both. Okay. Okay. That, as long as the H is a 4, that's not a 9, right? That's a 4?
Wait, where? Yeah, it's 4.
Yeah.
Sorry.
No, that's okay, it's just that some people make the, okay, so if we're looking at number 90, okay? Anna just took and changed the percent to grams, divided by the molar mass of carbon, and that gave her how many moles. Did the same thing for hydrogen and nitrogen, gave you moles of each one. But in order to determine whether or not it's a whole number ratio, you divide by the smallest value. Smallest value is 1.24. That gives you a ratio of 1 to 5 to 7. Well, that finds the empirical formula. So then she went and found the empirical formula mass being 81. The given, that 162 is given in the problem, 162, and then the divide by the 81, so that's 2. So the molecular formula is twice the empirical formula, so it's C10H14N2. Okay? Same basic thing now on number 92. Change. What?
I don't know why I wrote O.
Yeah, I do that all, because they're almost all oxygen, and
Yeah.
so I do the same thing. So change percent to grams, okay? Divide by the atomic mass of each one, gives you moles. Divide by the smallest value, and you get 1, 7, and 3, and that's the empirical formula. Now, they do not give the molecular formula or the molecular mass in this problem. Therefore, there's no way to calculate the molecular formula if the molecular mass is not given, or is it given?
I think so,
Wait, well, no, 92.
Yeah.
Yeah, it gives.
It does give.
Okay,
She
so-
has it written at the top.
The molar mass is 102, so now we have to go through and make sure on our empirical formula, so we really have part B on here, okay? So what steps do we need to take?
I got something
Oh,
different.
yeah, well, it asked for the molecular, so you had it right.
Oh, okay.
She thought it asked for empirical, so she stopped early, but it asked
Right.
for molecular.
And so it wants empirical and molecular, so now how do we take, this is the empirical formula. Okay, then Kruthika, you said you got something different?
Yeah, she rounded it to 3 because I think when you multiply it, you get 2.5.
Oh, really?
So I
Yeah.
multiplied it.
Okay, well, no, so that's very important, okay? So what does it come out to? You have 4 sig figs here. So when you divide this by 4, what do you get? I mean, we didn't cover this the other day, so that's why it's good to kind of go over
You
this.
get 2.501.
Okay, so 2.501. You cannot round that. The only time you can round this to the nearest whole number if it comes out to like 2.05, 2.01, 1.98. It needs to be within 0.05, really, just touch or go, to be able to round it, okay? If it's 2.5, what do we need to multiply by? Multiply by 2. But if we multiply that to keep everything in the same ratio, times 2 is equal to 14 is equal to 5 times 2 is equal to 2. When this happens, that just means that in the empirical formula, there's not a 1. everything has some number greater than 1 as far as how many atoms there are. So our empirical formula is actually going to be C5H14N2. Now, when you go and calculate the empirical formula mass of that, it's going to be 12 times 5 is 60, 74, 74 and 28 is going to equal 102 grams per mole. I don't need to be super accurate because it was only given as 102. So I can see that the empirical formula and the molecular formula are the same. Therefore, the empirical formula mass and the molecular mass are the same. Therefore, the empirical formula and molecular formula are also the same. Okay, so real important, and it's going to show up in this next one too. When you divide by the smallest, if you don't get close to a whole number, like within 0.05 is the actual maximum you can be away. First thing I do is carry it out to another sig fig. Make sure that I didn't round. Secondly, then you look for the common decimal. So if it came out to 2.25, that's going to be times 4, right? Because that's 1/4. So if it came out to 2.24, 2.26, we can pretty much figure that that's going to be 0.25. You multiply by 4. If it comes out to 2.33, 3.32, 3.34, that's a third. We're going to multiply by 3. Anything close to 2.5, 0.5 is going to multiply by 2. And then we're going to see in this next one, if you go 0.66, 0.65, 0.67, that's going to be 2/3, so we still multiply by 3. Okay, so you just look for your common fractions. Okay, so that's just an extra step that, because of time, I didn't get to really kind of go over. We didn't have any examples showing that. So when we look at number 93, it's the exact same situation. Change grams to mole, percent to grams, grams to moles, divide by the smallest, but this time it comes out to 2.67. So we have to multiply by 3, so the empirical formula is 8, 8, and 3, and then again, it's the same as the molecular formula. But in order to determine that, this molar mass has to be given, this 152, or the molecular mass, you have to know that in order to be able to do it.
Is there ever going to be a situation where you have to multiply it by like more than 3, like 4 or 5?
Rarely. I came across one that came out to 0.8, and you had to multiply it by 5. But most of the time, it's a 2 or a 3. Okay? Almost always, it's a 2 or a 3. Because the empirical formulas generally aren't going to have that massive number. They're going to be a simpler ratio. Does anybody have any questions about this? If any of y'all, watching this at home, if you have any questions, just, email me. Remind, a lot of y'all are doing Remind, and I'm responding to that as well. I get notifications on my phone. And so I'll be I think I was at Walmart when I was responding to you.
Really?
I was waiting on a prescription to get filled. And so I'm just sitting there. Okay, so that is one of the good things about virtual, is that you can answer it whenever. And some people were asking me questions last night and I was responding. Just feel free to do that. And Anna, what you do, just move that camera just to where it goes back to the middle. Right, kind of make sure 92 right there is kind of right in the middle of everything. All right.
I zoomed out a little bit.
Okay. And you guys, when you're watching on your Chromebook, you can zoom in too, can't you? On that, so if you can't see something on the board.
I think so. It's pretty clear right now.
Yeah. So, but this is going to be much more clear than any of the videos we did before.
Yeah.
So.
You kind of have like a wingspan, so like if you need extra room, you have.
Kinda what?
You have all the way into like half of 93.
Okay,
all the way
perfect.
to like the left.
Okay. Is there a way to hook that up to a monitor where I can actually kind of see what? Probably. All right. So what we want to do now, what you guys are dying to do now, what you're hoping for, is to take this up a notch. Because so far, we've been doing everything chemistry 1.
Let's do it.
Okay? So now let's go and take it up a notch to what we would consider an AP type problem. Okay? And this is gonna be called, well, I take a timeout. Before we do that, just to help you just kind of keep on this thing, let's just do one that is very similar to the lab. If you turn it over, you got the circled ones over there. But I don't want to do, number 108 and 109 are actually almost exact problems to what we did in the lab with Epsom salts, magnesium sulfate, and copper sulfate. So I don't want to kind of give those answers away as far as how to do that math directly. So let's look at number 107. The alum used in cooking is potassium aluminum sulfate hydrate. To find the value of X, you can heat a sample of the compound to drive off all the water and leave only the anhydrous form. Sounds familiar. Assume that you heat 4.74 grams of the hydrated compound and it loses 2.16 grams of water. What is the value of X? So this is worksheet number 107. So we have K, Al, SO4, I'm in 2 dot X H2O. Okay? And it says that we start, and that's gonna go, we're gonna heat that up, and it's gonna make KAl SO4 2 plus H2O liquid, X amount of it. Now it says, and this is the way I like to do problems, I like to put the information either right above or right below, so I know that it tells me that I have 4.74 grams. 4.74 grams of this, and it said that 2.16 grams of water was released. So how do I get this value?
4.74 minus.
Yeah, law of conservation of mass says atoms are neither created or destroyed, so just 4.74 on the left side has to equal 4.74 on the right side. So 4.74, so 74 minus 16 is 58, so it's going to equal 2.58 grams of this. This was 4.74 minus 2.16. Okay? So now what do I do with that?
Molar mass.
Of what?
The first one?
Okay? What values am I most concerned about? What am I trying to compare moles to moles? And this is where I didn't see your data, so I was kind of guessing some on your data. So this is where we can kind of double check to make sure that we use the right numbers. Okay? Because we want to compare the X is always going to be a mole ratio to whatever the coefficient is here. This is always going to be a 1. This is going to be some number greater, it could be a 1, but it's going to be 1, 2, 3, 4, 5, 6, 7. Some whole number ratio. Okay? So, I don't want this number right over here now. Once I get that, I don't need that number anymore. So what am I going to do?
The molar mass is the two ones.
This one.
Yeah.
Okay? And the molar mass of the water. So, I'm going to go just like we just did on the previous problems, but rather than doing individual elements, we're just going to do the two parts. Change grams to moles. 2.58 grams, KAl SO4 2 times 1 mole over the molar mass. So it's 39 and 27. 39 and 27 is equal to 56. 66. 39 and 27, 66. And then this is 64, 90, 96 times 2 is 188. 188 and 166.
484.
484. Is that what? Yeah.
Where's?
So just add them all up. Here, I'll tell you the numbers. 39.09 plus 27.0 plus 96 times 2.
258.09.
258? Okay? Now, that kind of makes more sense, because look, 2.58. So how many moles, and we can do this math in our head.
1.
No, if it was 258, it'd be 1, but it's 2.58, so it's
100.
100.01, right? But we get to have 3 sig figs, so it comes out exactly that many moles of KAlSO4 2. So what's my second step?
Moles of water.
Moles of water, 2.16 grams of water. Now this is one that you should just memorize, because we use it all the time. And water is going to be 1 mole over 18.02 grams. So somebody divide that one out for me, please.
Point 1198. Wait.
119, so 0.12.
Yeah.
Okay? Okay, so we have, again, if we want to, we divide by the smallest one, but because of the simple math here, this is 1, this is going to be, how much big times bigger is this one than that one? 12. 1 to 12. Okay? So this equals 1, this equals 12, so X is equal to 12, so my alum is actually KAlSO4 2.2 H2Os. Oh, but it came right back to me, so I get my rebound and get a second shot. But
Is it not 12 H2S? If X is 12?
I said 12. Everything about it was 12. I just didn't write 12. But yes, 12 H2O. Okay, so that's kind of an example of what you need to know. So you got to make sure on your numbers, because what you did is we weighed this into the evaporating dish here, approximately 2 grams, heated it up, weighed it again. Okay, so the amount that it went down was the water, but we got to make sure that we get this mass right. Okay, so you can either just use once you subtract the crucible, the evaporating dish, and so you know how many grams you have. This grams minus, make sure you're subtracting the crucible, the evaporating dish. Get how many grams of the substance, the hydrate actually was in there, minus grams of water. That'll give you grams of this. Okay? So, that's kind of a lab type sample question that are there. And if you look on the next 2, will be exactly like the lab if you want to practice. All right, now let's take it up a notch. Ooh, right before the bell rings. All right. Combustion problems. Okay? This is calculating the empirical or molecular formula when you burn something and collect the products. So on this same worksheet, if we look at number 101, it says that vitamin C is a compound containing the elements carbon, hydrogen, and oxygen. Determine the empirical formula of vitamin C from the following data. 4 milligrams of the vitamin is burned in oxygen to give 6 milligrams of CO2 and 1.632 milligrams of water. Okay? So, seems pretty complicated. But we know that vitamin C is CXHYOZ. We just know that it's composed of carbon, hydrogen, and oxygen. We just don't know how much of each one. When it burns, what does it combine with? Oxygen. So it's going to be plus O2 gas. This is a solid, it tells me. Okay, it's going to burn, and what's it make?
Carbon dioxide and water.
Carbon dioxide and water. Okay? Now it tells me that I start, now y'all, if everything's in milligrams and we divide it, it's all gonna give us the small numbers. I'm gonna just change this to grams and makes the numbers more workable, but it's because they're all milligrams, by multiplying by 1,000, we're not gonna do anything to change the ratio of these, okay? So I'm gonna have 4 grams. And it's gonna tell me that I'm gonna get 6 grams of CO2, and I'm gonna get 1.632 grams of water. I'm just multiplying everything by 1,000 to get just a number that's more comfortable to work with, so I don't have to use a bunch of decimal points. Now, believe it or not, given this information, you know everything you need to know in order to be able to find this empirical formula. We're not going to do anything new. Anybody want to venture a guess?
I guess you could use those two and find like how much of each element, and then like that has to stay the same over there.
Okay, you are very, very warm. Okay, I think you're actually on the right path here. We'll go specifically what you think we should do when we come back from the break. Okay? Now, those of you at home, I am not going to stop this so it's all one continuous file, but obviously you'll be able to fast forward through this 5 minutes at home. Okay? Because this is our break. So this is your time at home to get up and go to the bathroom, use your cell phone, because I know you haven't been on your cell phone at home. Okay? I'm going to go pop open another Mountain Dew. Restock. shutdown?
Like if we go back to normal schedule, people are gonna take pictures, post them. Jefferson County's already full virtual.
Well, they've been full virtual the whole time.
Yeah.
Well, yeah, I know,
I think it's
because,
gonna be fine.
but like,
I think we'll be good.
Yeah.
I think it'll be good too. You guys are resilient, you're tough.
I don't know.
You guys are gonna come and get me sick and then I'm gonna die. Y'all will be fine. No. I'm so tired of COVID, I kinda tell people, I kinda wish I could get it just so I could kick its butt. There's no guarantee,
There's a really good chance to like re-catch it. So it doesn't like, if you catch
Oh,
it,
yeah,
it
if you
doesn't
have
matter,
it, yeah.
you're still very vulnerable.
It's not like the flu where you get it and then like you can't get it again.
Well, what about all the antibodies that the
Yeah.
people that are getting over and they're using it to cure the other people?
That's only temporary. Like, that's like your own, very own vaccine.
I think
but-
you're listening to some very dark news, some very pessimistic news, okay? Now, I haven't heard of a lot of recidivism on this. I've heard, they talk about long haulers, the ones that think they're over it, but it just keeps going on and on and on. But, I'm just hoping and believing that, one and done for a season at least. Now, I'm sure you, like the flu, you can get it the next year too, but, so it's not a permanent, like chicken pox, once you get over it, you're over it. All right, Kruthika, explain now more of what you were talking about. You're right, we do want to use these.
Like kind of like what we just did, like just use those two in like the molar mass. I guess, and then like whatever numbers you get for these two, you would use the same. Like it has to balance out on the other side.
It does, but the problem is oxygen's coming in from another source, so that changes the mass of the oxygen, okay? But you are correct in that the two sides have to balance, right? So where did all of this carbon go? Assuming this burns completely, how much of this is left at the end? None, it's all over here, right? And so where did all this carbon go?
CO2.
To the CO2. That's the only place the carbon went to. Where is the only place the hydrogen went to? To the water. So we can use this to determine the number of grams of carbon present. Because our empirical formula problem, we had grams converted to moles, divided by the smallest, and we get the whole number. So we just need to know how many grams of carbon, how many grams of hydrogen, how many grams of oxygen we have in our 4 grams. How's it divvied up? And then we can change the moles and then find the empirical formula. So how can I find out how many grams of carbon are in 6 grams of CO2? No?
The ratio of the AMU of carbon to oxygen.
What do we call that, the type of problem that we just did? We just did the lab.
Hydrate?
We found, no, we didn't, it's not a hydrate, but we just found the percent oxygen in KClO3, right? How do we do that? 12 over 40, it's a percent composition. So carbon, for the carbon, it's 12.01 grams of carbon over 44.01 grams of CO2. Okay? So that's my percent. 12/44 of any sample of CO2 is always carbon. Now, we don't have to multiply by 100 because we would just divide back by 100. So we're just going to say times 6 grams of CO2. That's over and understood 1. Grams of CO2 cancel. That's going to leave me grams of carbon. Someone give me a value on that, please. Okay, we have 1.637, so 1.64 grams of carbon. If you want to carry one extra digit out, that's fine, but know how to round at the end. So what would we do for hydrogen?
Same thing with water.
But with water, so we know hydrogen is going to be 2.02 grams, because there's two of them, each one is 1.01, over 1.632, 1.6 grams of water, times, Stephen T. Hobbs, 18.02 grams, the molar mass of water, sorry, times 1.632 grams of water. Okay, so again, the part over the whole, the percent, 2/18 of any molecule of water is always hydrogen. So what does that come out to?
0.1829.
Grams of hydrogen. So now how can we get oxygen?
Oh, it'd be 183.
183.
How can we get oxygen now? Because the oxygen's in all four of them, so that makes it a little bit more complicated.
4.00 grams, CXHYOZ minus, 0.182 grams hydrogen minus 1.64 grams carbon.
Exactly right, because this whole thing weighs 4. We now know how much the carbon and the hydrogen weigh, so the rest of it must be the oxygen. So we simply subtract. And so we do exactly what Paul said, 4 grams minus 1.64 grams plus 0.183 grams, okay? Same thing Paul said, just written in a slightly different way. It doesn't matter if you just want to do the minus and the minus, so this is going to distribute anyway. So how many grams of oxygen do we get? 2.1, we'll say 7-8 grams of oxygen. You said 177,
Should be 1.
So it'd be 180.
1.8, that's what I meant to say.
Yeah.
Whew, you guys gotta keep me honest, Okay, now, once we're to this point, now it's just like the problems we just did on the board. Now we have grams of each element, and now all we gotta do is change the moles, divide by the smallest and get the mole ratio. Okay, so when we have a combustion problem like this, there's just kind of an extra step where we have to use percent composition to determine the grams of each substance. But once we have that, now it's going to be times 1 mole over 12.01 grams, 1 mole over 1.01 grams, 1 mole over 16.00 grams.
What about the O2?
This is coming in. We're only concerned about this here. So we know that all the carbon came from this, so I know that number's right. All the hydrogen went to here. So the oxygen is going to be different. It's going to add up, but we don't care about that. But we know that this sample was only 4 grams. So the rest of this sample had to be the oxygen. So I know that that's how much oxygen there was.
Alright.
In this, not the total amount in the,
Yeah,
in the
okay.
compound, in the reaction. Okay, so give me some numbers now. Moles of carbon.
0.137.
0.137 moles of carbon. Hydrogen,
0.181.
and lastly oxygen.
0.136.
Okay? So obviously you can see carbon and oxygen are going to be about the same. So we divide through by the smallest one, which is the 0.136. This is going to equal 1. This equals 1. Somebody.
1.33 for the.
1.33. So what does that mean we have to do?
Multiply by 3.
Multiply everything by 3. 3, 4, 3 is my empirical formula. So C3H4O3 is the empirical formula. Now, did they give us a more molecular mass on this, or we just have to find empirical formula?
It's just, it's empirical.
Okay, so just find the empirical formula. If they gave us the molecular mass in the problem, we could then go through and do the next steps and just calculate the molecular formula just like we did on the worksheet. The only thing different of this problem than the ones we did for homework is having to use the percent composition at the beginning to figure out how many grams of each element we have. And so there's always in a combustion, one of these goes to there, 2 out of the 3 are only gonna go to one place. And then you just by subtraction, you get the third. Now, even question number 100, it just says carbon and hydrogen. So there's only 2 things, just CXHY. So that one's even a little bit simpler than that in given if it's only 2. Okay? So just because you need to practice, why don't you try to do number 103? Just right there in your notes. 103. Once again, those of you at home will be able to, work on that 103 on your own, and then you can fast forward when we go over it. we getting stumped somewhere? Are we finished? I still see everybody kinda still working. Feel free to work with your partner or somebody at your table. I know you're socially distanced, but we can still talk to one another. Hey, well, what did you do after this point? Alright, so let's look at this. Okay, if you're not finished by now, it means you're struggling. So Ben, what do I do first?
You find the percent composition
Of
SI, which is,
Okay, so you go and you look at the molar mass of silicon, which is 28.09. 28.09 grams of silicon, divided by the molar mass of the whole thing, so add 32 to that, so it's gonna be 60.09 grams of SiO2. So 28/60ths of SiO2 is always silicon. Doesn't matter how much we have, but we have 12.02 grams of it, so we're gonna multiply by 12.02 grams of SiO2. Grams of SiO2 are gonna cancel, and we're gonna be left with grams of silicon. And how many grams of silicon do we get? 5.619 grams of silicon. Now we do the same thing. Now this time we don't have to do any subtraction. They give you both things here, so we're gonna do the same thing for hydrogen as we did over here. 2.02 grams of hydrogen over 18.02 grams of water times 5.40 grams of water. And that's gonna equal
0.605 grams of hydrogen.
0.605 grams of hydrogen. So now I have grams of each one. I need to know moles, so I just use the molar mass again. 1 mole over 28.09. 1 mole.
It's 0.6, not 0.06.
0.605. Alright, times 1.01 grams, and that's gonna equal 0.599 moles of hydrogen, and what does this top one equal?
0.2200.
Okay, so again, 0.599 is pretty darn close to 0.6. You got 0.2, 0.6, therefore this is a 1, this is a 3. So my empirical formula is SiH, I can do this, H3. This is my empirical formula. So how do I find my molecular formula?
The empirical formula mass.
Of SiH3, which is gonna be 28 plus 3, okay, so it's gonna be 31. And you can just go generic on this, and you don't have to carry it all out, because we're just trying to find the ratio, so I don't worry about decimal points when I do this one, okay? So I'm gonna go with the molar mass that's given, 62.2 divided by 31. I know that's gonna equal 2, so Si2H6 is the molecular formula. Okay?
Where did you get the 31 grams from?
The empirical formula, adding up the molar mass, the 28 plus 3 times 1. That's the empirical formula mass. So technically, it's gonna come out to 3.03, so it's gonna come out to 31.12. And then when you do that way, when you do it, it comes out to exactly 2. Alright. So, are you comfortable with this? Okay? So, what you need to know, I really wanna have a quiz tomorrow, which means you guys can take it at home and then just submit it. But over conversions, just dimensional analysis, sig figs, and then just these percent composition, empirical formula, you know, type problem. Well,
Would we like write out our work on, I mean, like, we would write out our work on a separate sheet of paper?
Yeah,
Would
and
we
just can't-
take a picture?
Yeah.
Yeah, okay.
or if, a lot of times my tests and quizzes are right on,
Okay.
so if you can print it out,
Okay.
print it and
Yeah.
write on the actual
Okay.
test and whatever, and then cam scan it and submit it. I'm trying to decide what all I wanna include, cause what we're, you know, we're gonna, shoot, really, we're not gonna be back until next Thursday. I'm supposed to keep you all on pace.
Have we been okay so far?
We're okay, I mean, I don't know, but see, I don't know how well everybody's understanding everything, because I only see y'all 2 days, we haven't had hardly any real measurement, and even giving y'all a quiz, you guys are gonna be at home, I'm gonna say, hey, try to do this without looking at anything, because the people that are here are gonna have to do it without looking at anything. But, what I'll probably do is just make it open note, just because it's gotta be fair, cause, I mean, even though I trust y'all implicitly, there will be, you know, you'll be at home, you'll have your stuff and whatever. Just cause I just wanna make sure that we can do the dimensional analysis, that we can do the sig figs, that we're good. We need to have a test over all of chapter 1 and 2, which is gonna include atomic number, mass number, average atomic weight, you know. So part of me is just saying, let's just do some practice problems and then just get ready for the big test on Thursday and Friday of next week, you know?
Have you considered Canvas, the tests on Canvas?
Well, how's that gonna be any different?
It doesn't let you go to another tab.
Yeah, you can monitor what we do and we can.
Yeah, but you're gonna have your phone right there.
I guess.
Yeah.
Okay, I mean, I could do it via Google Meet as well, you know, where everybody has to have the camera pointed on them and whatever, but,
Miss Barlow's doing that.
Yeah.
Like, we have a test today in computer science, and we have to, for the people at home, it's all on Canvas, and all on Canvas for people at school, but you have to be in the Google Meet
yeah,
to take it, or else we get a 0.
right. And so, I mean, I was considering doing all that, but, you know,
It's a lot of work.
it's just a lot of work. I'm just, hey, to me, I'm in survival mode for the next 2 weeks. And then we can kind of get back to face and take the test like we're normally gonna take it here in class all at the same time. And it's gonna work. Just watch on Classroom. I'm off next period. I'm gonna just kind of look and see what I can have. Tentatively prepare for a quiz tomorrow. It may just be more like a graded for accuracy worksheet type thing, because, again, you'll be at home and I'm gonna just kind of make it to where, you know, you can use your notes and go back, but can you do these problems, you know, given that, okay? And it's more gonna be dimensional analysis, sig figs, and a lot of the stuff we did in chapter 1 that we haven't done in a week, just to kind of get back at that, okay?
Are we gonna have any of like the homogeneous, like heterogeneous stuff on there?
I mean, as far as, information, like qualitative questions,
Yeah.
short answer, no, that's good, this is gonna be a math. That'll be on the test. Comprehension survey, by the way, is what I like to refer to them as, comprehension survey. How well are you understanding the material, okay? Now, we are not going to do the naming section at the end of this chapter, okay? Chapter 2. I think as far as time is concerned, we learned how to name last year, but naming isn't a big part. On the AP, you'll never have to say, what is the name of this, or name this compound. They'll throw names out there, but you should be able to recognize, pretty much you don't need to know that. You already covered it, so for the sake of time, I'm just gonna skip over that part. Normally I just do it as a separate unit and give you a quiz over the naming and the ions. But this year we're just gonna work at learning, remembering how to do it, remembering these ions over here, and getting real familiar with nitrate and sulfate and acetate and all the common polyatomic ions. And we'll just talk about naming just generically as we go through the year, okay? All this stuff that I did on combustion problems, all this is the beginning actually of chapter 3, okay? So that's kind of where we're gonna be ending up at as far as for the test. And then the rest of chapter 3 is gonna be all about our favorite stoichiometry, okay? So, I was gonna do one more thing. All right, so over here, now, these are just more practice problems that are actually in your textbook. Okay, this is all about empirical and molecular formula, and these last 3 are all combustion problems. So if you want to do more practice of those, then you can look in the book and kind of work through and do one more of those. As a matter of fact, I'll shine one up here, but let's look at number, I just want you to have more practice. We've got time. This is the hardest one, so the more you do of these, the more comfortable you'll be with them. So let's just go ahead in your notes. Let's just look at number 55 right now. If you want to pull that up in your Chromebook, you can, but I'll shine it up here.
Are we gonna have the combustion on the quiz tomorrow?
No.
So it's everything but like what we did in class today, right now?
Well, yeah, and I may or may not put empirical and molecular formulas on there. I may just save that for the test as well, and just do more of the conversions, dimensional analysis, sig figs. And I may throw in just a table for the filling in atomic number, mass number, number of protons, neutrons, electrons, like we did in the back of the end of chapter 1, I think, or end of chapter 2, they had the little tables, and with ions and those type of things. So that's the simple stuff that I want you to just make sure everybody knows how to do. Okay, so here's number 55. Is that big enough for everybody to read? Just do A. Actually, just do B. Just do B. As you're doing this in your notebook, you might want to put that this is page 116, number 55, just so if you want to go back and look, you have the book at home, you know, as you're studying. Okay, so as we're looking at this, just, if you're not finished, just keep working. Notice I did not erase much of the previous problem, okay? In purple now is the new information. So everything that's given here, 0.1005 grams of the menthol, it's gonna make 0.2829 grams carbon dioxide, 0.1159 grams of the other. So the format is going to be exactly the same. So to get the grams of carbon, I'm gonna take the percent composition of carbon, but I'm gonna multiply it by the sample of carbon dioxide. So when I do 1244s times this, how many grams of carbon do I get?
0.07721.
0.0.
7721.
Okay, we'll just say we stick with 3. Although we really should have 4. Okay? And then do the exact same thing for the water, 2/18 times the mass of the water, 0.1159 grams of water, and that comes out to 0.0130 grams of hydrogen. And so then how do we get grams of oxygen? Subtracted from this. So it's gonna be 0.1005 grams minus the sum of 0.07721 plus 0.0130, and that equals
0.01029.
03. No, we're supposed to have 4 sig figs, 29 grams. Okay? So now we have grams, so now we're at the same point, so now we just use the molar mass of each element, okay, to convert to moles. So how many moles of carbon do I get?
I got 0.006428.
So what do you think? I got
43.
Yeah, so I just rounded.
Yeah, just round it. Again, we have 4 sig figs, so these zeros are not significant at the beginning, so to carry it out 4 sig figs, that's grams of carbon. Actually, that's moles of carbon. Okay? And then when we divide this one out, it comes out to 0.0129. And we only have 3 sig figs on this one, so we'll just keep 3, but we still have a good number of decimals. And then on the oxygen,
6.431 times 10 to the negative 4.
okay, so 0.000 644. Can we get one more digit?
6431 is what I got. Or is that-
6431.
Yeah.
Okay? So now we have a mole ratio, but it's kind of a crazy looking one. We can't just look and kind of see what it is. So we divide by the smallest one. Oxygen is the smallest one. So we're going to divide this by 0.0006431, 0.0006431. This is going to equal 1. What do these equal?
20 and 10.
20 and 10. So this one is 10. This one is 20. So our empirical formula is C10H20O1. Okay? So that's equal to my empirical formula. So how do I get my molecular formula? Find the EFM. 10 times 12 is 120, 140, plus 16 is 156. So 156 divided by 156, which you can just do in your head, you don't really have to show, that equals 1. So that means that this is also the molecular formula. Okay? So, if there is a question on the AP test dealing with percent composition and empirical formulas, they're almost always this type. Okay? It is using percent composition. figuring out, well, how many grams of carbon are in this sample here? Well, it's 1244 times whatever the mass of the sample is, and we did kind of a practice problem with that when we did percent composition, okay? Finding just the empirical formula. Now, there is a way to go directly to the molecular formula from the, not going through the empirical formula. I choose not to even share that with you. It is in the textbook, but because this works for every type of problem, empirical formula, molecular formula, combustion problems, this step works. The other way only works if you're finding molecular formula and they give you the molecular mass. To find the empirical formula, you gotta come back and do it this way. So I don't even bother to share that other method with you, but there are definitely more than one way to do this, and as long as you show good science, then you're fine. Okay? Alright, so those of you watching at home, there's a lot of dead time today that you fast forward through, but you really do need to be practicing doing these problems on your own. So hopefully at home, you're trying some of these and making sure you know how to do them, because we are going to be having a test. And I mean, I hate to say this, but I mean, I think the test will probably be Friday of next week.
Would it be Thursday for us?
Well, no, I'm just gonna do Friday and you'll do it at home. And what I'm gonna do on the quiz tomorrow and the test is that you'll take it, now, for the test, you'll take it both periods. But for the quiz tomorrow, since it's gonna be a video for the rest, I'll let you take the quiz. We gotta do it first period, so I was gonna try and let you sleep in a little bit, but we're gonna do it. So I'm gonna start it at 8:20, okay? And then I'm gonna give probably 30 to 35 minutes to kind of just do it. Okay, that way you still have to kind of know how to do it on your own, okay? And so if you're at home, you'll do it there. Now full-time virtual, you're gonna do it first period as well, okay?